Hi, I'm Florian Felten, and today I'm going to quickly present our work in progress on hyperparameter optimization for multi-objective reinforcement learning. So this is the result of work with my wonderful co-authors, and we are all from the University of Luxembourg. And this work was presented at the multi-objective decision-making workshop at ECAI this year. So let us first start with a bit of context to see where we come from. So multi-objective reinforcement learning was hard to reproduce and apply in the real world in the recent years due to the fact that we lack standardized environments and standardized and open source implementation of the state-of-the-art algorithms. So this meant that as a researcher, you had to re-implement the environments and the algorithms and try to reproduce the research paper results in order to be able to compare your new algorithm or new method to the existing baselines. So we started working on this to solve this problem. So we designed Gymnasium, which is a set of environments under standardized API, and this aimed at solving the first problem. And then we started talking about this on Twitter, and I said, no, we need baselines algorithm which respect the API, and we're good to roll. So we're good to roll on the research and do good research. So we started to work on a project called MRL Baseline, which is essentially a collection of multi-objective reinforcement learning algorithms, and this solved the point two. So as you can see, we have algorithms capable of learning Pareto set of policies, which is essentially policies leading to various trade-offs in the objective space. For example, here the half cheetah problem actually involves making trade-off between energy efficiency and velocity. And so in learning various ways of running, the half cheetah leads to different trade-offs. So now we have a proper ecosystem for MRL. We have environments under standard API, we have open source algorithms, and we have also open benchmark results. And so, as I said, we're good to roll now, aren't we? But it turns out that it's not that simple and it's not done yet, because multi-objective RL does not work out of the box for every problem. So when we designed MRL baselines, we started to apply the algorithms on existing benchmarks, where the combination of the algorithms and the benchmark had never been done before. So for example, we applied envelope Q-learning on minecart, which are two state-of-the-art entities, but they were never applied together. And then we realized that envelope does not learn on this environment. And then so we could go and draw the conclusion that maybe envelope is a weak algorithm, or maybe envelope was overfit to the problems that were presented in its paper, or I don't know. But actually, it turns out that it was a problem of hyperparameters, and we believe that hyperparameter optimization is going to solve actually multiple problems. First, for real-world applications. So whenever you encounter problems like this, well, you might be tempted to try to tune the algorithm by hand, but it turns out that some algorithms have dozens of hyperparameters. And if you're not a domain expert, so a multi-objective RL expert, or even the algorithm designer, you don't really have much ideas on how to tune these hyperparameters. So this really hinders the applicability of these methods into the real-world problems. And also for science, because often as algorithms designer, we have what we call the designer's bias, which is basically that we focus on beating the existing baselines to show that our algorithm is the best. So this actually involves implicitly spending time tuning our algorithms. So we will implicitly tune our algorithms on the problems that we are currently studying. And I think and actually I'm not the only one to think that, but we should spend the same amount of time tuning existing baselines on the problems that we study to make the comparisons fairer. And that's exactly what hyperparameter optimization aims at solving. So it's an automated way to find hyperparameter values which lead to good results. given a certain budget. So having the same budget for baselines and new algorithms ensure that the comparisons are fair, and having an automated process allows people which are not experts in the field to try to tune these hyperparameters. So we started formalizing the problem in the paper. So we have given a multi-objective algorithm A that is parameterized by zeta, which are the hyperparameters, and this algorithm outputs a Pareto set of policies pi and its corresponding Pareto front. And so now we want to find the hyperparameter values which lead to good performance based on the Pareto front and Pareto set of policies. So this is HPO, and MRL, of course, is just you take hyperparameter values and an environment, and then you learn and you return Pareto set of policies and Pareto front. So this looks like a simple optimization problem, but it's actually way harder than it looks, because we have expensive evaluation. So for example, multi-objective reinforcement learning, so each run will take hours or days. So you cannot really just go and try all of the hyperparameter values that are possible in the hyperparameter space. Also, this problem is constrained, so some hyperparameter values are not compatible with each other, and they might lead to erratic behaviors in the MRL algorithm. So you need to take care of that. Also, reinforcement learning in general is a stochastic process. So if you repeat the algorithm on various seeds, you get different results. So even when you look for hyperparameters, you need to look for hyperparameters based on different runs, based on different seeds. And also, the way you optimize also will depend on what you want in the end. For example, if you want to optimize for performance, then you will probably try to maximize the average performance. However, if you want to have an algorithm which behaves where the performance of the algorithm does not drop drastically for some seed, you want to minimize the deviation of the performance. Also, you need to avoid overfitting the algorithm to the seeds that you use in the search process, because you will probably use the hyperparameter values that you found on different seeds, and you don't want the algorithm to completely drop on those new seeds. Finally, actually, hyperparameter optimization for multi-objective reinforcement learning is a multi-objective problem. Why? Because MRL usually return a Pareto-based output, which is usually a Pareto front, and this is a set of points, and we do not have a direct way to compare this set of points together. And so we usually, in the multi-objective literature, we usually rely on performance indicators, and these performance indicators usually try to assess two criteria. So first one is convergence, so it's how good the policies are, so how close to an optimal Pareto front they are. And the second one is diversity, so how wide the range of compromises that you present to the user is. And you want generally a wide array of compromises to present. So here we present a procedure to solve the problem of HPO for MRL, which is divided into two phases. So the first phase is a searching phase where you run the algorithm for various hyperparameter values on different seeds to try to find a good hyperparameter values. So you instantiate an optimizer, and for a given budget, you take hyperparameter values from the optimizer, and then you train the multi-objective reinforcement learning algorithm using these hyperparameters on various seeds. So this process typically returns a list of Pareto fronts, and then you use multi-objective indicator to convert the Pareto fronts into scalars. So now you have a list of scalars. And finally, you used an aggregator to aggregate that list and reduce it to a single scalar and report it to the optimizer. And so you go on and you try different hyperparameters and report that to the optimizer. And now we have the validation phase, which is essentially taking the best hyperparameter values that you have seen during the optimization and try it on different seeds. So we do that, but we train for a longer time this time on different seeds from the searching seeds, so this avoids the overfitting problem. And then we report using multi-objective indicators, and we report that to the user, and we report the best hyperparameter values. So we applied this procedure to the scenario that I presented earlier. So we used a Bayesian optimizer and optimized for 15 hyperparameters. So this is just impossible for a human to do by hand. And we let the optimizer run for 48 hours on 3 different seeds for each set of hyperparameter values. We use the hypervolume indicator, which is hybrid, so it has the ability to assess for convergence and diversity at the same time, so that's why we used it. And finally, we use average as aggregator. And for the validation phase, we ran the algorithm on 10 seeds which were different from the searching seeds for a longer budget. And now we can see that the results are completely different. So the tuned hyperparameters version is in blue, while the default, so the first one that I presented, is in orange. And you can see that the algorithm doesn't behave at all the same. And so actually envelope is not a bad algorithm, it just had very bad hyperparameters. So that's why we really want to emphasize that we shouldn't draw conclusions without tuning the hyperparameters. And the cherry on the cake in this process, because I think that it uses a lot of computational resource to do the hyperparameter optimization at the moment, but actually you can reuse information from that searching process. If you take the search memory, so you take all of the hyperparameter values as features, and as label you put the average, so the final performance, so in our case it's average hypervolume, then you have what looks like a supervised learning data set. And on that you can actually use sensitivity analysis tools or existing supervised learning methods to analyze these searching logs. And so, for example, you can actually determine which hyperparameters are the most important to tune, and you can also analyze basically your multi-objective reinforcement learning algorithms. And this is a very new process to understand what works and what doesn't in multi-objective reinforcement learning, and I think it's going to play a key role in the future. And so already a conclusion and future direction. So I quickly presented the new field of HPO for MRL, which allows for fairer comparisons and easier applicability of the method through new problems. We proposed an early solution which has been already merged to MRL baselines. So as future step, what we want to do is obviously conduct more experiments, so different algorithms and different environments. And also I think that this process is going to play a key role into an empirical study of multi-objective reinforcement learning, because we cannot really compare algorithms without tuning all of the hyperparameters. And I think that sensitivity analysis is going to also help us to understand what matters in multi-objective RL. For example, and now we also have new questions. For example, do you tune hyperparameters generalized to unseen but close environments? So for example, if I optimize for a Mijoko environment, will it work well for another Mijoko environment? And finally, it's also interesting to see that hyperparameters can also determine algorithmic strategies. So for example, the Bellman update. And thus, we might be able to automatically generate multi-objective reinforcement learning algorithms for a given problem using this process of HPO. So thank you for your attention, and I'm looking forward to hear from you if you want to discuss this.